Have you ever wondered about the invisible force that literally holds our world together? I mean, it's the energy hidden inside every single atom, and it's what powers the battery in your phone right now. Today, we're diving into that force, electrostatic potential energy.
So, to get our heads in the right space, let's think about this for a second. Picture a massive storm cloud, just churning in the sky, crackling with power. Before that huge, brilliant bolt of lightning flashes across the sky, where is all that energy? The answer, it turns out, is all about energy that's stored just by where things are positioned.
So to really get what's happening in that storm cloud, we actually need to start with something a lot more familiar. It turns out that the simple act of fighting against a force, well, that's the whole secret to storing up potential energy.
And this same principle connects two totally different worlds. Think about it. When you lift a book off the floor, you're working against gravity, right? All that effort you put in gets stored as gravitational potential energy. It's the exact same idea with electricity. When you force two positive charges together, charges that naturally want to fly apart, you're fighting their repulsion, and the work you do gets stored as electrostatic potential energy. Now, physicists have a name for forces like gravity and the electrostatic force. They call them conservative forces. All that really means is that the energy you put in to fight them isn't lost. It can be perfectly stored and then perfectly recovered later. The energy is just waiting.
Okay, so keeping that gravity analogy in mind, we can finally define what electrostatic potential energy actually is. And I promise, even though the name sounds a bit complicated, the core idea is incredibly simple. All right, I know that formal definitions sound super academic, right? Infinitely far apart. What does that even mean? Well, here's a better way to think about it. Imagine you're a builder and your materials are electric charges. The electrostatic potential energy is just the total amount of work it costs you to push and pull all those charges into their final arrangement. It's the energy cost of building the system.
So the process always starts from a clean slate. When charges are super far apart, infinitely far, you could say, they can't feel each other, so we just say their potential energy is zero. But the moment you start bringing one charge closer to another, you have to do work. And that work doesn't just vanish, it gets pumped right into the system and stored as potential energy.
Now, you might see this word slowly pop up in textbooks and think, why on earth does that matter? Well, it's absolutely critical, because we want to isolate just the potential energy. See, if we move the charge really fast, some of our work would turn into the energy of motion, kinetic energy. By moving it nice and slow, we make sure that every single bit of our effort gets perfectly converted and stored as potential energy. Okay, time to look at the formula. But please, don't think of this as just another equation you have to memorize. Think of it more like a really short, really elegant story that tells you everything you need to know about how this energy behaves. So here it is. U is our potential energy, Q1 and Q2 are the amounts of charge, and R is how far apart they are. Simple enough. But the real story here, the part that tells us everything, is hidden in the signs, whether the charges are positive or negative. That's what tells us if the system is stable or if it's ready to fly apart.
Here's how that story unfolds. If you have two charges that are alike, say two positives or two negatives, the potential energy works out to be positive. And a positive energy means the system is tense, it's repulsive. It's like a compressed spring just waiting for a chance to expand. But if you have opposite charges, the potential energy becomes negative. And that means the system is attractive, it's stable. The charges actually want to be near each other.
And this brings us to one of the most powerful ideas in all of physics. Negative energy means stability. It's like a ball that's rolled down into a valley. It's settled at the bottom, in a more stable, lower energy state. When charges have a negative potential energy, they've found their valley. They're bound together.
So that all works great for two charges. But what about more complicated setups? Like the actual molecules that make up our world. Let's take a look at how this whole concept scales up.
And this is where things get really elegant. To find the total energy of a system with a whole bunch of charges, you don't need some new complicated formula. You just have to calculate the energy for every single possible pair of charges, and then you just add them all up. That's it. So for example, if you have three charges, you just have to look at the three unique pairs. You calculate the energy between charge 1 and 2, then the energy between 2 and 3, and finally the energy between 1 and 3. Add those three numbers together, and that's it. You've got the total energy for the whole system. Now, obviously, as you add more charges, the number of pairs you have to consider grows pretty fast. But thankfully, there's even a handy little formula for this.
For any number of charges, which we call n, this formula tells you exactly how many pairs you need to sum up. It's just a systematic way to make sure you account for every single interaction.
Okay, so we've covered the definitions, we've looked at the math, we've seen how to build systems. But let's ask the most important question. Why should you care about any of this? Well, it's because this seemingly abstract concept is the fundamental reason that matter exists at all.
I mean, the implications are absolutely massive. That negative potential energy between an atom's nucleus and its electrons, that's what holds the atom together. The energy you get from chemical reactions, that's just charges rearranging themselves into more stable, lower energy configurations. And the power in your battery, it's nothing more than stored potential energy in a clever chemical setup, just waiting for you to release it.
So I'm going to leave you with this final thought. We've seen over and over again that negative potential energy creates stability. It binds things together. So what does it mean that the atoms in your body, in the chair you're sitting on, in the very air you're breathing, are all held together by this exact principle? It suggests that on a deep, fundamental level, our universe is built on attraction and stability. Something to think about.